Hello everyone, my name is Sujin Kathari and today I'll be presenting Lab 3 Black Hole Lab. The goal of this lab is to find the mass of a black hole in regards to a star in orbital motion from position data combining concepts we have learned and ultimately Newton's gravitational force law. So here's Newton's force law and here's the gravitational constant g, which is 6.7 times 10 to the negative 11 newtons times meters over kilogram squared. We obtain everything in this formula by using the given position data to find velocities and then using those velocities to find the momentum and then breaking up the momentum into parallel and perpendicular components to find the total net force and represent it on a computational model. We will instruct Python to evaluate the magnitude of the position squared as we already have the position of the black hole and position data of the star. Let's look at our code now. As we know, we need some initial conditions which were given to us, and these were the star's mass and position of the black hole, shown here. Down here, we instruct Python to import the position data from the CSV file that we downloaded from Coursera. In this first while loop, where I have calculate velocity from data, we instruct Python to calculate the velocities of the star on its trajectory orbiting the black hole. In the second while loop, what we first do is we find v initial and then v final. After we find v initial and v final, we are able to find p initial and p final, which is simply the mass times the velocity, or the star's mass times velocity. Once we find the initial and final values of both p and v, we can find delta v and delta p. We have learned that the net force of an object in curvilinear motion can be broken down to parallel and perpendicular forces. First, we just define dp dt as delta p over delta t. From the momentum principle, we know that F net is equal to dp dt. Now let's calculate the dp dt parallel. Before that, let me show you some equations to make everything a little bit more clear. We know that F net is equal to dp over dt, and we know that F net can be broken down to parallel and perpendicular components. Similarly, dp dt can too. The reason this represents the parallel portion is because we're taking the change of the magnitude of the momentum rather than the direction of the momentum. Therefore, for the perpendicular, the object can either speed up or slow down, as we learned in the videos, while for a perpendicular force, the object can change direction. That's why we take the change of direction for perpendicular and not in parallel. So that's basically what we did in our code here. To find dp dt parallel, we found p hat, or the direction vector. We found the change in the magnitude with respect to time, and then we multiplied those two together, and that gave us our parallel force. We know that the parallel force is equal to the perpendicular net force, or the dp dt parallel is equal to the net force parallel, and that's exactly what we've defined here. Next, because we have dp dt, and we have dp dt parallel, we simply subtract dp dt minus dp dt parallel to give us dp dt perpendicular. And once we find dp dt perpendicular, we know that that is also equal to the f net perpendicular. The reason we can do that is because we know that the parallel and the perpendicular forces give you the overall dp dt. So simply, if we subtract the total dp dt minus the parallel which we obtained, we can find the perpendicular force, or the perpendicular momentum. At this portion of the code, we have successfully used the positions given to us in the CSV file to find the velocities, and then use the velocities to find the momentums, and then use the momentum to find the total net force as the perpendicular and parallel portions will add to equal to the total net force. Scrolling down to my print statement, in my print statement, I asked Python to print the magnitude of the parallel and the perpendicular net forces. You'll see that when these two are printed, that they add up to the total magnitude of the overall net force. I also ask it to print the mass of the black hole, as at this point we have everything we need to do to find the mass of the black hole, and Python simply does it for us. I do this with two important lines of code. This line represents Newton's gravitational law rearranged to find the mass of the black hole. This is the magnitude, r squared, in the denominator that we usually see. It's star.pos minus the position of the black hole, squared. Here's the star, mass of the star, and here's the magnitude of the net force that we found. Let's watch my code run now. So the black sphere represents the black hole. The black arrow represents the parallel force, and the blue arrow represents the perpendicular force. The yellow arrow represents the F net gravitational force to the black hole, and we can see that it will always point to the black hole, as the perpendicular and parallel components will always add up to the net force. And the mass of the black hole turns out to be 1.99 times 10 to the 31st. We see that the parallel and the perpendicular components right here actually add up to be this value, which is the total net force, 3.05 times 10 to the 26th, and it is added up by this parallel component and the perpendicular component. So let's take a look at the two questions we were supposed to answer. So for the first question, what exactly is the difference between F net and dp dt and their components if we say that they are apparently equal to each other according to the momentum principle? And the answer is that dp dt equals F net is derived from the momentum principle, and that dp dt is something that can be calculated from the observed position data. However, F net is the force that is causing the observed motion, and it is not something that we can measure directly. Therefore, it is different because F net is something that is qualitative, while dp dt is something that is quantitative. So for the second question, it's asking, if the black hole was swapped but the positions remain the same, would the mass of the new black hole be different from the original one? And the answer is no. That because literally nothing has changed besides the black hole. This means that the original positions are the same, the velocity and the momentums are the exact same for the star orbiting. That means the total net force is also going to be the same. That means the new black hole is probably just going to have the same mass as the old one. Well, that's the end of my lab. If you have any questions or comments, please leave them in the question box below. And thank you so much for watching.